Okay, can you see the slide?
Boleh, Prof.
Okay. So this is the lecture number 9. We will talk more into classifiers. So in the previous lecture, we talked about clustering, k-means clustering, hierarchical clustering dengan DB scan. So that is more on the unsupervised. And then we talk about neural network, in which neural network can perform the supervised and also at the same time unsupervised learning. Okay, so we focus also on perceptron because this is the basic classifier for binary classification. So today we will cover decision tree. So decision tree is supervised learning in which used for classification. So the ingredient behind the decision tree is how do we actually construct the tree, and then how do we interpret the result that we have. Okay. So since the name of the classifier is called decision tree, so your solution will look like a tree when we look at the diagram below here. So we want to decide whether we want to accept the offer of
Sorry, Prof.
yes, the slide is
We
not
cannot.
moving. Kan?
The slide not in full screen. Yeah.
Okay. Let me share the whole screen. I stop this. Okay. Let me know if you cannot see the slide or the slide is static. Okay. Can you see the slide on the front page?
Yes, Prof. Can.
Yes, Prof.
Okay. So based on the name of the classifier decision tree, so the main issue that we want to look at this classifier is we want to know how actually they construct the tree. Okay. So if we look at the diagram here, can you see the diagram? The trees, or still on the front page?
We can see the tree, Prof.
Okay. So the decision that we need to make is how actually we decide or perform the classification using binary, not using the decision tree. So in this example, we say, okay, we have to decide whether we want to accept a new job. So at the bottom here, you can see the decision that we make, accept or decline. So this is basically the class label. So we start from the root here. Then we look at the condition for each of the node. So if the salary is at least 50,000, then if yes, we go here. If no, we reject the offer. And then we also look at the condition if the commute is more than 1 hour. If more than an hour, then we decline. If no, we go to here. Then the last one is, do they offer coffee? Then if yes, then you accept. So it seems that all these three conditions must be fulfilled, which is salary is at least 50,000, commute less than 1 hour, and then offer coffee. Okay. So the question that we want to ask here: how do we decide the condition for the root tree, and what are the values? So in this case, this the model itself consists of a series of logical decisions that we need to fulfill. So this is split into branches that indicate the decision choice. So yang bawah ni, this is what we call the label of the decision tree, which is the final decision. So for example, if we try to separate the blue circle and the red rectangle, so we can always have this like where the W10 is no, X1 is always greater than W10. So we go here, and then if your X2 is always greater than W20, then you say this is red. Okay, so this is how we draw a line to separate the blue circle and the red rectangle. Okay, so the node that we have here, this is the attribute that we use, and then we look at the value to split in order to maximize the purity of each of the partition of the data set here. Because if we set the value here, then of course we will split the data into subset depending on the values of your attribute here. Okay, so if you have a single variable, then we use that variable, and we decide where to split them. We could also have more than two subset by having n-way split. So n-way split is if you have n possible values. Okay. We also could have multivariate. We all use all the attribute that we have, so it's more than one. And for the leaf, they always represent the class label. Okay, and for regression, the value for that particular one is the average ataupun what we call it the standard deviation. So this is used for regression tree. Okay, so for us to decide where to split and what are the values, we use this learning greedy learning, which is find the best split recursively, which means that we try every possible variable that we have, and then we also try every possible values of each of the variable and decide where to which variable that we want to use to split them. Okay, so we will go through that one later on. Okay, so the way they construct the tree is they will call recursive partitioning, in which they will keep separating or partitioning your data until they find a subset that represent a single label, class label. Okay, so it used the feature values to split the data into smaller and smaller subset of similar classes. So similar classes means you have high purity of one label. Okay, so this is what we call divide and conquer. So we choose the best candidate feature each time until a stopping criterion is reached. Okay? So these are the conditions that you can stop splitting your tree if all the example at one node have the same class, because there is no point of splitting them anymore. They have, all the member belong to same class. Or you do not have any remaining features to distinguish among example. Contohnya, you have used all the features that you have in your dataset. No more features can be used. Okay. And the last one is we made set or predefine the size of your tree, which is the depth of the tree. Okay, so we don't want to grow your tree too much because it will be more complex in terms of defining the logical decision that we have. So we want to limit them. So if we set the threshold to be 4 depth of 3, so that means you only go down up to 4 stages using 4 different conditions. Okay. Okay. So when we talk about true positive and true negative, we look at here. So the entropy here referring to purity of your data set. So which means that if your entropy is 1, that means all your sample in that group belong to a single class. Okay. So that means if you are here, that means your entropy is no. Yes, if sorry, I repeat again, the entropy must be 0 for 100% pure of having same class. So when you are here, your entropy is 0. Okay, and your positive class is 100%. So 100%, all your sample have correctly classified as positive sample. And if you are here, so that means half of your sample belong to positive class and the other one belong to negative class because you have 0.5 here. So for that reason, your entropy is 1. So your entropy will be 1 if you have 50-50. 50-50 of label belong to different label. Okay, so the since we are using positive and negative sample, so the formula will be like this, in which this is the total entropy. This is the entropy for the positive side. This is the entropy for the negative sample. So we add up this together. So if you have 100 of your positive sample here, this is 0. So that means your entropy will be 0. But if you have 50 and if you have 50, so your entropy will be 1. Okay. So when it comes to looking at the purity of your group, we always look at for the entropy because entropy represents purity. Okay. So for example, like this, imagine we have this group. So we have 5A and then 3B. So if you look at the probability of having class A is 5/8 and the probability of having B is 3.8. Okay. So if we use the formula that we have previously, so this is the formula. Okay, since we have A and B, that means we have 2 parts here, A and B. And then if we substitute the number here, so this is for the A, this is for the B, A and B. So the total is 0.95. 0.95 is high, that means they are not pure. Okay, So this is how we determine the purity of your one group. Okay. Okay. Now let's suppose we have this data set, and then we look at the outlook. Okay. So the outlook has three unique variables: sunny, overcast, and rain. And then if we split your data according to the value of this attribute outlook, so we will have um, 3 no and 2 yes. So this is when we check this one. So this is 1, 2. We look into sunny first. So we have 3 no and 2 yeses, kan? Okay. So if you look at for the overcast, so we have 1, 2 yes, and then 3, 4. So we have 4 yeses. Okay. And the rain is the remaining. So this is our splitting. Um, the three group is called subset of your full data set. So if we use Outlook to split the data, we have three unique value for Outlook, and these are the distribution of your data according to the unique value of Outlook. Okay. So how do we compute? Now we have three group here. So we need to use this formula, and now our K here is 3. Okay. So the first one that we need to look at, we look at the sunny first, and then the overcast, and then the rain later on. Okay. For the sunny here, so we compute the entropy for this by using the probability of um, having sunny is no, and also having sunny is yes. Okay. So in this case, we are looking at, because in here, so no, we only have 3, so 3/5, and then for the yes, we have 2. So this is the entropy of our first subset here for sunny. And then for the overcast, we have all four yeses, so we have 0. Okay. And then for this one, if you look at this one, we have 3 and 2. So this is similar to what we have here. So we can assume that the value for the I rain would be 0.96. Okay. So now we have the entropy for the three subset. So to combine them, because we want to have a single value to represent the entropy of all the three subset of data. So we will use this as our weightage for each of the group that we have, and this is the entropy for each of the group that we have. Okay. So how do we apply this one? Let me, okay. Before that, so if we apply this formula to compute the total here, let me erase this. Okay, so to compute the total entropy here, so we would have the weightage for this one is 5 over, we have 14, so 5 over 14. So that means we have 5 over 14 times the entropy of that subset, we have this. Okay, and then we plus, this is 4/14, but the value for the entropy is 0, so we ignore that one. And the next one is this one, so basically 5/14 times 0.96. Okay, so that is the total. Okay, so this is just to give you the run through. Okay, after splitting, we have the entropy for each of the group, and how do we actually combine all the entropy to become a single entropy to represent the effect before and after splitting them. Okay, so that goes to the second formula that we have. So this is the info gain um, that we define as the entropy before you splitting minus the entropy after you splitting. So that's why we need to have a single value to represent the entropy of your subset of data. So this is before and this is after. Okay. So what we want to have is we want to maximize the info gain, because for example, if you have the entropy is, for example, 0.9, and then once you split them, you expect them to have same group for same level. So we expect this one will reduce the entropy. So the info gain that we have is 0.2. So we want to minimize this and maximize the info gain that we have. Okay. Okay. So for example, this one, we split the data, but we have this. So this is the error. So this is very good because we able to split the positive and the green circle. So what we want to know here is before and after splitting that. Okay? So for the purity, we say this is very pure. This is 50-50. So this is very impure because they have mixed. This is less impure. This is maximum purity or minimum impurity. So this is not pure. Okay. So to compute the total entropy, like I mentioned just now, we have to have a weightage to represent that subset of data. So this is the entropy of that particular subset. So what we want to do is we want to total up all the entropy that we have by multiplying the weightage of that particular subset with the entropy that we have. So that is the total entropy when you have split them. Okay. Okay, let's go back to here. So basically we are showing here, before the splitting, we have our data, all of this. They are in one group. Okay. So this is belong to here before you splitting. So before you splitting, we have how many yes and no? So we have 5 no and no. We have how many? So in the beginning, we have 1, 2, 3, 4, 5. Okay. So the total is how many? So this is 5, 14 lah. Okay. So di sini we are repeating the same thing. So this one is the entropy for this first subset. This is the entropy for the second one. And this is the entropy for this one. Okay. So to add up the value, we just basically take the weightage. This is the weightage for this 5/14. This is 5/14. And this is 4/14. Okay. So we just add up the value, we get this. So this is basically the value for when you split the data. But before you split the data, basically we have this. So this is how do we get this? This is before we splitting. So basically we have 5/14 log 2, 5/14. So this is for the no, and then plus 9/14 log 2, 9/14. Okay, so this is all in minus. So if you compute this one, they basically give you 0.53, and then this part here will give you 0.41. So this is before the splitting. So before the splitting minus after the splitting, we get this, how much we gain. Okay. So this is used to measure which variable you want to use, because in this example, we are using this example. Just use this feature to split. So we can try again for temperature or humidity or wind. So we will choose the attribute that will maximize the information gain that we have. Okay. Okay. Another example is for this one. So imagine that we have this data set. So we have 5 no and 5 yes. So before we splitting, because initially we have this 5 and 5, so this is our entropy. Okay, so since we have 50/50, so the entropy is 1. Okay, now we want to use the count here to split. So we have um, A, B, C, and D. So for the A, we have 2/10. This is the weight. And then this is for the class for no. And then for the second one, we have 3/10. That is the weightage. And then we have 2 no's and 1 yes. So this is for the no's. This is for the yes. Okay. Are you guys following me? Okay. So for this one, for the C part, we have 3/10, and then all of them belong to yes. So we have one part only, which is 3/3 log 2 base 3/3. And the last one is we have 1 yes, 1 no, but the weightage is 2/10. So we have this. Okay. So the question that we want to ask is, since we have two variables here, so this will give you some value. Okay, so this one will give you some value. So you repeat again for the total here. Okay, so where you split the data here, 1, 2, 3, and 4. So you will repeat again and you compute the entropy for splitting the data using total. Then whichever give you higher information gain, so you will decide that variable to be used to split your data to start the root of your decision tree. Okay, okay, let's take a look at one example here. So we have this risky bank loan. Okay, So these are the steps. Okay, the first one is collecting the data set. So we will get this data set from this website. So the data that we have will looks like this. So this one is default, means they are not paying your um, loan. Okay, and these are some of the attributes that we can extract for the client that we have. So based on these features, we want to model the no and yes here. If yes means they are not paying, if no means they are paying your loan. Okay, so over here we read the data from this .csv. I will provide this file. Okay, and over here we say string as vector, meaning that your string of character will be treated as label. So we have what we have, this checking balance. We also have credit history. We have purpose. So all the string of character will be changed to label. Okay, housing and so on. Okay, so if you want to play around with the variable, so you can always use the table, and then you say, okay, we are reading into credit, so we can access the variable using the dollar sign. So this sini we have credit and then the dollar sign checking balance. So this one basically give you how many record having this features value for the checking balance. Okay, this one also will give you the value for and the number of column, the number of record that belong to having saving balance using this variable. Okay, so we have unknown here, so we need to clean that one. Okay, so we could also use summary to look at the range of value that you have. So this is the month loan duration. The summary will give you mean, first quartile, median, mean, and then third quartile and maximum. So this is the maximum value, minimum value. So we can repeat for the amount and so on. Okay, so this is just to uh, give you an overview how your data looks like. Okay, and this one telling that 30% of your staff will no 30% from your client will have high potential to be defaulted, means they are not paying the loan. Okay. Okay. So what we will do, we will do sampling here. So we do sampling 90% to be used for the training, 10% only to be used for testing. So over here, I'm doing sampling. From 1000, I get 900. So what I have here is basically 900 unique ID, the row ID. Okay. And then so I will take all those 900 values and put in the training, and the remaining I will put in the test. So this is 90%, this is 10%. Okay, so if you look at the proportion of the table that we have for the default here, so we have 70%, 30%, and if you look at the for the test, this is for the training here, and this is for the test. So we also have similar distribution of instant having no and yes. So this is a good training and testing data set. So once we split them into training, and testing data set. Okay, now we can call the decision tree. They call it C50. So we install first, then we upload into the memory. After that, then we can use them. So over here, we call the C5.0 and we give the training data set and also list of class. And the trial here is an optional number of control, the number of boosting iteration. So this is used to create and assemble. Okay, so over here, one means we only have one classifier, and the cost here is an optional metric specifying costs associated with various type of error. So di sini we just put null saja. Okay, so what we do, we call the C5.0. We provide them with the training data set kecuali row number 17. Okay, we minus the row 17 because they consist of the class label. We need to provide them in the next one. Because in here we need the training data set and also the class. By default, this is 1. Okay, so the model that we have will be stored here. So we can look at the tree, but if we look at the tree, okay, they say here if your checking balance is this value, so that means not defaulted. Okay, so over here they tell you how many record correctly classified and how many record which is incorrectly classified. Okay, okay, so based on this, we can interpret that, okay, if the checking account is unknown or greater than 200 Dutch money, then classify as not likely to default. So that is where you have here. Checking balance is greater than 200 Dutch money or unknown, then not likely to default. If your checking balance is less than 0 Dutch money and or you're having this value and credit history is perfect, so that means you are highly to not to pay the loan. Okay, so this is the finding that we have. If your checking balance is less than 0 Dutch money or between 1 and 200 and your credit history is perfect or very good, then classify as likely to default. Meaning that this characteristic telling you they are high risk of not being able to pay the loan that we have. Okay, so if you look at the accuracy, how do we know the accuracy here? So we will look at because we have the 900 cases for the training. So in this case we have the error is 14.48. We say the model correctly classified all but 133, so we have this. So the error is 133 divided by 900, so we have 14.8. Okay. Okay. So this is true positive, true negative. So your error is here. Okay. So that's where you get the 133. Okay. So what happened here? This is the class A, and they are predicted as no. This is case A, the case B. So this is the true positive. This is B and B. So this is true negative. Okay. We could also look plot the cross table. So plot the cross table here. So if the label is the actual label for default is no and predicted as no, so this is true positive, and this is true negative. Okay, so this is what uh, they are false, but so this is false positive, this is false negative. Okay. Okay. So how do we improve this one? We can increase the number of trial. So we use the adaptive boosting. Uh, Adaptive boosting is just like you have one classifier here, and then you create another one classifier here, and so on, and so on, and so on. Okay. So that is the number that we can use. Example that we have this one. So trial 10, that means we are having 10 classifier arranged in sequential. Okay, so when you have this, so this is what we call the forest, random forest. Okay, so we, we, we can put this one because the default is 1, so accuracy just now is around, accuracy is around 85. So once we increase this trial to 10, so your accuracy would be higher. So di sini your error rate is 3.8, so your accuracy is 96, 95.2 lang. Okay, so that's how we can improve the model performance. Okay, so in summary, so this session explained to you how do you compute the entropy. Okay, how do you come up with the information gain? Based on these two values, two formula, we can decide to select which feature or which column we want to start. No, we want to use to split your data. Okay, so that's how decision tree is constructed based on choosing the right features to split your data. Okay. Any specific question you want to ask?